So we've got a lot to get through today, but I think our goal here is to give you an overview of what a work loop is, both from a sort of theoretical and empirical sense, but then also to see one in action, and then to look at the data from it and actually try to plot it. So this will start with a little bit of a tutorial kind of thing, and then we'll actually go see Casey do an actual experiment with all the problems and difficulties that can arise with that, so you can get to see the whole thing. And then we will give you data. We'll do the cooking show thing where instead of giving you the actual data from that experiment, we have pre-prepared data from another experiment that we will have given to you, and you can take a look at that. And we'll have a challenge for you at the end. For the last part of this workshop, you will need access to something that you can open a CSV file in, like MATLAB or Python, or even R, and you'll need to be able to try and plot some very simple data, okay? All right, so what I'm going to do is I'm actually going to start off by talking about what a work loop is and why we use it. And so in IMSI, not everybody may be familiar with muscles and how we try to make measurements from them. So this is like the first workshop on how to do some of that characterization beyond some of the very sort of simple static measures that we've made in the past. So what I'm actually going to do is I'm going to stop sharing that slide. And I'm going to instead switch to my iPad because I think it makes a little bit more sense to just do this effectively as a whiteboard. All right, and now everybody should be able to see that. And hi. All right, so my name is Simon Sponberg. I'm a faculty member here at Georgia Tech, and I'm also one of the co-PIs for IMSI. And so what I want to talk about today is how do we characterize what a muscle's function is? And so for a lot of us in our experiments, we will either measure a muscle's properties in vivo or take the muscle out of the animal and measure the forces that it's producing under different conditions. And so I want you to start off this workshop by thinking about what would happen if you had a muscle that you had taken out of an animal. And I'll apologize in advance for my graphical qualities, which are somewhat limited. So we've got a muscle here, right? And if we start off with the muscle, what we'll oftentimes do is let's imagine we take the muscle out and we fix it on one side. So that gives us an anchor point, all right? And then we're going to try to measure various properties of the muscle on the other side. And usually what we're trying to measure with our experiments is the force that the muscle produces. And usually we think of that force in the shortening direction. So how much force the muscle would pull on like a strain gauge or a muscle lever or some kind of force transducer. And then we can also talk about the length of the muscle. The muscle at rest, we'll call that L naught, and we'll call the length axis in this direction here on the x-axis. Okay. So we can measure usually the two properties of a muscle that we can measure in these kinds of experiments are the length of the muscle and the force that it's producing. And oftentimes we'll set one of those and measure the other one. So for a long time, people have tried to characterize the function of muscle by making these force measurements. And the classic ways to do this are sort of threefold. There's three kinds of measurements we would make from a muscle. The first of those would be a twitch response. And in a twitch response, what we would do is we would hold the muscle at a constant length, let's say L naught, and we would measure the force that the muscle produces. So we'll put that on the y-axis in response to, and we'll measure that force over time in response to some kind of stimulation that we provide. And usually when we talk about a twitch response, what we mean is that we're sending a single brief pulse or spike of activity to the muscle. Now, if you're not familiar with the physiology side of neurons and muscles, they oftentimes communicate with these digital pulses called action potentials. And so oftentimes what we do in a muscle is we play in a single action potential, if we're talking about a single motor unit, or perhaps a single brief burst of stimulus that only lasts a millisecond or something. So you can imagine that I have a stimulus occurring somewhere like here in time. In a mathematical sense, you could think of that as just a little delta function. So what's going to happen is the muscle is going to be sitting here producing, let's say, zero force. It could be some offset force, but let's say it's at its resting length with zero force production there. And so it'll click along here producing zero force. And then when it's stimulated, the force will rise and then fall. And that response of force over time is called a twitch response. And what we could do in addition to that is we might play in multiple spikes of activity, like let's say 2 spikes, and then we might get a larger response that takes a while longer to fall off. Okay, but classically the twitch response is in response to a single pulse of activation. All right, and it characterizes the muscle's force versus time properties. The second way that we would oftentimes characterize a muscle is with what's called the force length curve. This is also sometimes called the length tension curve because tension is force along the axial line of a long thin thing. But we're going to call it force length here because I think it's a little easier to understand. And in a force length curve, what we'll oftentimes do is we'll measure the force that the muscle produces under some level of activation as a function of different lengths that we pull that muscle to. And so plotting it as a force length response makes it seem like what we're going to do is monitor the force and pull it to different lengths continuously. But that's not how a classic force length curve is usually measured. Usually when we make these measurements in the classical way of doing a force length curve is we will set the muscle to a specific length, activate it at that length, and then take a maximum force measurement. And then we'll let the muscle relax. We'll activate, we'll stretch it to a new length. We'll measure the force at that point, and we'll get another point on this graph. So this graph isn't measured continuously. Instead, we'll oftentimes see various points on this graph from individual experiments like this. And that's because the force length curve was originally designed to test hypotheses about the sliding filament theory, the idea, the molecular basis for how muscle is contracting by the sliding of actin and myosin. And so classically, I won't go through these too much because I want to get on to the main part of this presentation, but classically there would be like 4 phases to the force length curve. 2, 3, 4, 1, corresponding to the different degrees of overlap of filaments at the molecular level. But it would create this classic sort of force length curve. And this would be the active curve. And muscle would also produce some amount of passive force or tension, which would usually rise up at some intermediate level. And so that would be the passive and the active contributions to the force length curve. And so empirically, if we did this in experiment, what we would typically measure would be a sum of these two. And we would get a curve that looks something like this. And that would be the activated force length curve of a muscle. What I want to really emphasize here, though, is this is again taken from a bunch of static measurements. So this is not a good approximation of necessarily of what the muscle would do under dynamic conditions when it's actively changing length and it's activated. This is a single measurement taken at different length points, and that's going to become really important in a minute. The final thing that we would classically do to measure and characterize a muscle is to measure its force velocity curve. So as a function of it shortening with different velocities, we can make another plot. And usually here velocity would be in the shortening direction. So here would be, for example, a resting velocity of 0. And as we shorten it faster and faster, the amount of force that the muscle would produce would fall off. But we could also have lengthening stretches, which typically produce more force. So this area is called, this is a lengthening stretch. In muscle terms, we call that an eccentric motion. And here would be shortening or concentric. And then the sort of last thing that we could do is we could multiply force by velocity and get a measure of the power of the muscle. And we could plot the power as a function of velocity. And that would look like something that would peak in between here. Okay. Actually, I really should, to be a little more rigorous, so I'll just draw this. This is usually just for the shortening. So I'll draw it just for that portion of the plot. Okay. Good. Now, when we do these measurements for velocity, again, it's not taken continuously over a dynamic contraction. Instead, what we do is we take these measurements under what are called isotonic conditions. So in the previous case, in the force length curve, we took them at each measurement at a constant length or an isometric condition. And for the force velocity curve, we take measurements under isotonic conditions. So usually what we do is we hang a known load off of the muscle, we activate the muscle, and then we release the load, and we measure the maximum shortening velocity that that muscle can produce against that load. Okay, so again, it's made up of a bunch of series of individual points that we measure from different parameters in the experiment. So again, because this is a maximum force produced at a steady velocity, this is called a steady state measurement, which is a little sounds a little counterintuitive because or a steady measurement because you think, well, the object is going to accelerate up to some maximum velocity, but since we're only measuring it at that steady place where the velocity is constant and the muscle is producing as much force as it can against it, that's why this is still a steady measurement of muscle function. So that's one big caveat of these ways of measuring muscle, is that they're usually steady measurements. The twitch and the force length curve are isometric. The force velocity curve is isotonic. The other big caveat is they're oftentimes done under single twitches or maximum activation. So the classic force length curve, you activate the muscle to its maximum and then measure its force and its length properties. Same thing with the force velocity curve. Now you can do submaximal force length and force velocity curves, but they're still going to be steady measurements. So and the reason why this was developed this way is, again, these kinds of characterization of muscle really weren't meant originally. They weren't designed originally as experiments to test muscles function in dynamic conditions. They were designed as experiments to test mechanisms about muscles' underlying physiological properties, like the sliding filament hypothesis. And so when people got interested in characterizing muscles' function under more physiological conditions, we needed a different tool for doing this. And this is a tool that Bob Josephson developed based off of early experiments by Machen and Pringle called the work loop method. And the idea here is, instead of taking static measurements at different lengths, let's measure the force that the muscle produces as the muscle goes through some kind of trajectory of length change, like what would happen during a cyclical movement. So to think about that, I want to pivot us to think about what would happen in a really sort of simplified model. Let's just say we had a leg, a single jointed leg with a hip and some kind of hip extensor here. So when the limb is at its most extended most flex point at the beginning of stance, this muscle would be very long. And then as it pulls the muscle through its stance phase, pulls the leg through its stance phase, the muscle would shorten. Okay. So for this muscle, we could then measure its length as a function of time. And let's just say, for the sake of simplification, that the resting length of this muscle, or the operational length that around this muscle, around which is operating, is L naught, is going to be right at the center of this muscle's length trajectory. So the muscle would start out stretched, and then it would shorten, and then it would lengthen again, and then it would shorten again, and then it would lengthen again. And so in the part of the stride where where this muscle is lengthening, that's going to be the swing part of the stride, where the leg is swinging back to its front position. So this would be going from here to here is stance, and then going back is swing. And then the muscle is going to shorten during stance. Okay. So now let's think about the force that that muscle is producing. And this is where it gets really important. So I'm going to pull out just this one cycle. And the first thing that I'm going to do is I'm going to plot the length again. And I'll plot that in blue here. And so the length for one swing stance cycle is going to look something like, and I'm going to draw this pretty carefully. Actually, I'm going to do that one more time. So I try and get a nice sinusoid out of it. To the best of my drawing abilities, which are somewhat limited. Okay. Good. All right. And so again, L naught will be somewhere right in the middle here. So this will be the length plot. And now on top of that, I'm going to plot the force that the muscle produces. Okay. So at the beginning of swing, if this is an extensor muscle, we might think that the muscle still has some residual force, and that force is going to die down during swing, such that about halfway through swing, it's producing zero net force. And so then a little time after stance initiates is, remember that this part, the second part of this phase is going to be stance, is where we might find sort of maximum force production. And so the force for this might look something, oops, like, okay. So what I want to consider now are 4 points on this plot. We're going to consider the beginning of swing, the midpoint in swing where force is minimum, the transition to stance, and halfway through stance. And remember, because this is periodic, if I just label these times in the cycle, or what we would call the phases of the motion, then this point here is going to be 1 again, right? That lines up with the same point. The force and the length have the same values. So now what Josephson did is he realized that you could take this, and instead of plotting force and length versus time, you could plot force versus length again. But now, unlike the force length curve, instead of doing a bunch of static measurements, now we can plot it continuously over this cycle. So what we're going to do is we're going to look at the midpoint in length here, L naught. We're going to look at the minimum length, L min, and the maximum length, L max, and we'll plot the force, and it will be generally above 0 here. Force I was doing in red. Okay, and so let's just plot these points onto the plot on the right. So in the first case, we're at L min, but the force is not at 0. So at some point like right here. So that's point number 1. Then we go to our, and then we go about halfway through the cycle, and the force reaches a minimum. It might not necessarily reach 0. Then when we get to our maximum length here, the force has redeveloped some force. But then we start going back, and halfway back through stance, we have our maximum force up here, 0.4. And so now we can connect these points, and we get a loop. because the motion of the muscle and the motion of the limb is periodic. So this is a loop in force length space. And what we're going to see is that that's going to give us a value of work. And I'll show you how we calculate work from this loop in just a second. But I first want to talk about why we would want to calculate work at all, right? So what is work or mechanical work? Mechanical, so yeah, let me actually go to the next page. So what is work? And here I'll specifically mean mechanical work in the physics sense. So work equals the change of energy that something does on the system. So the work that a muscle does on a load is how much energy in that load of that object that is producing the load, how much energy changes in that system. And specifically, it's the mechanical energy. And so this is composed usually of two different types of energy, the kinetic energy and the change in potential energy. Okay. We usually talk about two different kinds of common potential energy. One is working against gravity. That would be gravitational potential energy. So we can draw that as delta UG. And one is the change in elastic energy, like if you're working to load energy into a spring. So delta UE for elastic. Okay. So when you do work on the system, there's several different things you could do. You could raise the system up, right? Changing its gravitational potential energy. You could, if you did positive work on the system, you could store energy in an elastic structure like a spring or a tendon, increasing UE. Or you could accelerate the system, changing its velocity and increasing the kinetic energy in the system. So those are sort of three different ways that you could have the effect of doing work. And if you think about what a muscle does to a system, it can do all three of those things, right? So that's how a muscle is doing work. So what we're really interested in is work is going to measure the change in the mechanical energy of the system on which the muscle is acting. So how do we calculate work? Well, many of you from early physics classes or biomechanics texts might remember that work is sometimes written as force times the distance, or even worse, I think, force times the length. And if you ever see these equations, please don't use these. These are not right. Okay. What many of you may have used practically before is work is equal to force times the change in length. And this is better. In some cases, this is correct, but this is still not right in a general sense. And you might say, okay, Simon's just being an annoying pedantic physicist at this point in time. I started off as an experimental biologist. I still consider myself that, even though I partially work in a physics department now. But I think it's really important to actually write out for a minute what the formal equation is for work, because it really reminds us about what we have to pay attention to. And so work is actually equal to the dot product of force and the change in position. And we have to remember that force and the change in position are vectors. And remember, because work is a change in energy, energy is not a vector. It doesn't have a direction. It's a property of the system. So work is also a scalar. And this is really important because force and change in position have directions, but work is a scalar. And so we need to multiply those vectors in a particular way, in this case, using a dot product or a scalar product. That's why that dot is really important. And why is that so important to consider? It's because the only contribution of force and change in position of the system that is relevant for work is when the two are parallel. So if I apply a force in one direction and the system is changing its position in another direction, the work is not equal to force times delta x. It's equal to the dot product of those. It's equal to the two components that lie in the same direction. So the component of delta x that lies parallel to f. So we can calculate W as the magnitude of F times the magnitude of delta x in the direction that's parallel to f. Well, delta x parallel is going to be equal to delta x times the cosine of the angle between these, right? So that's just a trigonometric identity, cosine theta. And so work is going to be equal to the magnitude of the force times the magnitude of the change in direction, generally, not just the parallel component, times the cosine of the angle between them. And that's a really important part to remember, because this equation is only correct when the two are exactly parallel to each other. And that's not always the case, right? Muscles sometimes act at angles with respect to joints or loads. And sometimes when we're taking measurements, we may not measure our change in length in the same axis as our force. So you can think about this like when you implant sonomicrometry crystals. If you've done that, the change in length vector of the sonomicrometry crystals might not be perfectly aligned with your force vector. And then to figure out the work that the muscle is actually doing, you have to think about this angle here. So I like to remind us to always think about forces and changes in positions as vectors, because that helps us do a better experiment and think of a pitfall. I've reviewed multiple papers before that have made this mistake, that have not considered the fact that the forces and the change in position may not be operating in the same direction. So now that we've done all that and we've figured out the careful accounting for this, there's one more really annoying pitfall to watch out for when we're calculating work from an experiment. And I'll tell you, I spent so many hours of my PhD trying to fiddle with negative signs in MATLAB and trying to figure out why my work was coming out negative or positive when it should, given the physical setup of the system, I knew it should be one sign or the other. And the reason why that is because we've created a little bit of a weird construction here, which is when I drew this original picture of the muscle being attached to an anchor point, I said, let's measure the force in this direction and call this positive F, right? But then we talked about L being in this direction, and length would be positive going in the lengthening direction, right? You get longer as you stretch. So our force and our length are not pointed in the same direction. What we really need to think about when we're thinking about work is we need to think about delta x. Which direction is the system changing? Okay. And in this case, to keep our sign convention correct, we really need positive delta x to also be in the shortening direction. Okay. So in that case, we're going to think of delta x being equal to minus delta L. And this is a very helpful sign convention if you remember it. If you screw this up, you'll get the wrong sign for the work that you calculate, right? We need the same sign convention through here. The reason why this is actually works out this way is because when we're calculating work, what we're actually calculating is the work the muscle does on the system. And so if we have a load that this muscle is pulling on, then the force and the displacement of that load are both going to be positive to the left. Or they could both be positive to the right, that would be fine too. But the important thing is that the force and the displacement have to be pointed in the same direction. Like that. Unless there's another force acting on it that's pulling it in the opposite direction that the muscle is resisting, in which case it will do negative work and that will turn out correctly. So this is an important sign convention that we need to get them right. So now what we can do is we can think of the net work, not net work, but net work that the muscle does on the system. And for that, what we can do is we can look over this force length loop. What is the product of the change in x and the force that's being produced. So here's my zero force value. I'll just draw this again. We go from 0.1 to 0.2 to 0.3 to 0.4, and that's going to create a loop. Two, three, four. And now the work that the net work that's going to be produced is going to be equal to the integral, because the force and length are changing in time now, of f dot dx. So it's become an integral and a differential here, as opposed to a delta x. And that's because it's continuously changing in time. And as long as dx and f are parallel to each other, then this will be equal to f, the scalar, the magnitude of work, times the dx, the magnitude of the change in position. But that's only true only when parallel. Okay. So now what we can do is we can look at, let's calculate the work done during swing. Well, that's going to be the area under this curve as the muscle is lengthened out during swing. And since this is an extensor muscle, that makes a lot of sense. We have a positive force. So force is positive. Delta x is negative because our length is increasing. And remember, delta x is negative delta L. And so our work during swing is going to be negative. And that makes a lot of sense, right? Any force that the extensor muscle is producing during swing is going to be resisting the flexion of the hip. What about during stance? Well, during stance, let's do this in a different color, actually. During stance, that's going to be the area under this curve. And here we're going to have positive force. Our delta x is going to be positive now, and our work during stance is going to be positive. And what you'll notice is that this curve goes in this direction. It goes counterclockwise around the loop. And when it goes counterclockwise around the loop like that, what that means is that the work done during stance is going to be greater than the work done during swing. And the net work is going to be positive. So this is a positive work loop. It produces net work on the system. It will positively increase the energy of the system. So just to summarize, the net work is equal to the sum of the swing work and the stance work. I've done this for terrestrial locomotion. You can, of course, do this for flight and swimming as well. All right, the last thing that I just want to do is to show you the other kinds of work loops that you can have, and then we'll go over to the demo. So what happens if we have a muscle that produces more force when it's resisting motion, when it's resisting stretch? So this might be like your quadricep when you go downhill. This is going to be an idealized version. I know Monica's listening, so with apologies to Monica and all the complications that can go into leg muscles, let's look at sort of an idealized quad going downhill. It might actually during stance, it might only produce a small amount of force. So now it's going to go in the other direction. So this is the stance phase. And then it'll produce a large amount of force resisting the motion of the leg or dissipating energy during swing phase. And so in this case now, the muscle would start out here. It would shorten first, and then it would re-lengthen. And in this case, the work loop is going in the other direction. It's going in a clockwise direction. And if you calculate out the area during swing, is now the work during swing is now this area, and the work during stance is this area. And so there's net negative work being done here. And so in this case, what that means is that this muscle is acting like a brake. It's dissipating energy from the system. But that's not the only kind of work loop we could have. What about a work loop that looks like this? So here's a work loop that has very little area inside the loop. And so what that means is that the network is going to be approximately zero. But that doesn't mean that this muscle isn't doing anything, right? As you stretch it out, it's producing a large amount of force. And as it shortens, it produces a large amount of force. And in fact, this is very similar to, and if you look at this, you could even say if there's just a simple line here, right? Then you could say, well, it looks like F is related to delta L by some constant slope, let's call it K. And if we remember that delta L equals minus delta X, that means that this equals minus K delta X. And if you remember an equation for F equals minus K delta X, that's called Hooke's law. That's the equation for a linear spring. And so this is what a work loop for a linear spring would look like. It does no net work because it stores and returns an equal amount of energy without any dissipation or net positive work being done. And so muscles can sometimes act like springs if they have work loops that are shaped like this. But that's not the only way to get net zero work. You could also have net zero work by having a force length curve that looks like this. Here, this muscle is not changing length at all, right? But it does develop force. And you could also have one where the muscle doesn't produce force at all. It's just relaxed, but it changes length. It's a relaxed muscle that's just being pulled on by a load. So this would be a strut because it just transmits force at a constant length. And this would just be a compliant muscle. And in both these cases, the net work is zero. And in fact, you might see a muscle that has a combination of these that has a period of changing length with no force, and then a period where it doesn't change length, but it produces a large amount of force. And the final one I want to draw is a muscle that it acts first like a motor and then acts like a brake. So maybe during swing, it doesn't produce a significant amount of force. The force is effectively zero. But then it first produces a lot of positive force and then a lot of negative force. So that would be against a load. It resists it doesn't have enough force to resist the load. Or actually, we could just offset this all down to zero below. And so then we have a positive and a negative phase to the work loop, where the sign we're going first counterclockwise and then clockwise. And if those two regions are exactly zero, again, you could have the network equal to zero. So if you just tell us that we have a muscle that produces zero net work, that doesn't actually tell you what the function of that muscle is. It could be a spring, could be a strut, it could be something like this that acts like a motor and then a brake. Okay. So the very last thing that I want to say is that one of the other ways that you would plot this sometimes is instead of measuring force versus length, we sometimes might measure the stress of a muscle, denoted as sigma, versus its strain, denoted as epsilon. And this is very similar to a force length curve, but sigma is the stress, which is the force per area, and epsilon is the strain, which is the change in position over the length, the resting length of the muscle L naught. And so in this case, if we have stress times strain or integrated together, we would get a force over an area times a delta X over L naught. And if we look at that, this product up here is the net work. Whoops. And the product on the denominator is an area times the length. That's going to be a volume, right? And if we assume a density of water, which is usually a pretty good approximation, this is approximately equal to the net work over the mass of the system. And so when we plot a stress strain curve, what we oftentimes get is instead of the work done, we'll get the mass specific work, or the work that is normalized to the mass, oftentimes to the mass of the muscle, though this could also be sometimes normalized to the mass of the body, and you have to be careful which value is being reported in the literature when you get mass specific work. If it's a stress strain curve in a technical sense, it should be the mass of the object that is doing the work. So in this case, the muscle or the muscle tendon unit. And the one last thing that we might calculate is the mechanical power in the system. That's the rate at which work is done. And so that's the power is going to be equal to the net work over the amount of time that it takes. So, but if this is a periodic cycle, then one period of motion is 1 over the frequency of that. And so power is equal to the net work times the steady state frequency. Okay. So that's where I want to end this. That's my little tutorial on work loops and how to sort of calculate the work from them and how to think about them. I want to stop my sharing now. And as I'm pulling up some the slides to introduce the tutorial we're going to do, I can also take any questions if there are any. You can also post them in the chat. I'm looking at that now. And Casey's going to go over and is going to be prepping the is going to be prepping the demos so that we can take about 15-20 minutes to look at that. Any questions?
Sounds good, Simon.
Before I introduce this? Okay. It's always hard to tell on Zoom if people are actually watching, but I see a Minds watch party, so that's good. Hopefully folks are awake there.
Simon, this is Jill. I have a quick question.
Yep.
So if you're interested, let's say in contact, and you think about contact as having different phases, let's say run. Okay. Could you talk a little bit about how you take these concepts and look, say, and you want to give that a go?
Sure.
Where I'm going.
I think the simplest thing to say is one of the really complicated things about terrestrial locomotion is this idea of contact. And it actually really changes how we should interpret a work loop, because what is the load the muscle is doing work on? Well, if the limb is in contact with the ground, then effectively what that muscle is going to do work on is the body, because it's going to produce it's going to push on the ground, get a ground reaction force of the ground pushing back, and that's going to do work on the body. So effectively, actually, what the muscle does is it does work on the ground, and then the earth does work back on the body, right? But if the muscle is in the air, if the limb is in the air, then the muscle, like during that swing phase, the negative work of the swing phase is actually probably best thought of as acting against the system of the limb by itself, because that's what's swinging forward, because it has no contact with the ground. And so oftentimes what you're doing there is you're dissipating energy from the inertia of the sort of inertial energy of the limb as it's swinging through the air. And so I glossed over that here a little bit, but I think sometimes the original work loops were done in flight, which is nice, or in swimming, because there you don't have a change in contact. But when we interpret work loops in a terrestrial case, it's actually pretty tricky, because the target of that work changes. The way that you define your system, you have to be very careful of when you're thinking about it in stance versus swing, because you have ground contact in one case and not in the other. So I don't know if that fully answered your question, but definitely something to be really careful about.
Yep. And I also think about it's teams of muscles instead of one. So
absolutely.
So does it help to put at least the context of changes in muscle lengths and rate of change of lengths?
Yeah, so you usually analyze a work loop in the context of a specific muscle, but what's causing that muscle to lengthen? Well, what's causing that muscle to lengthen is all of the other muscles and the load acting against it. So oftentimes if a muscle is acting like a brake, what it is doing is it's dissipating energy that other muscles are putting into the system. And that may sound like a bad idea, but from a control perspective, that could actually be really good, right?
Right.
And so we usually analyze that with respect to a single muscle, but you can do work loops on joints as a whole. Anything that you can plot the total force on and measure the length change of, and that could be an angular change, not just a length change, you can do a work loop on. And Monica's done a bunch of those as well.
Great, thank you.
As many people on here. Thank you. Yeah, that's a good clarification. Okay. I want to just give a quick overview to, this will just take a few moments. I just want to orient you to what you're going to see when we walk into the other room, and then I'm going to try and take you over to a live experiment, okay? So what Casey's doing in the other room is he's going to show you a work loop on a flight muscle of a large hawk moth, which is a moth that's about the size of the palm of your hand. And so these moths have really cool muscles because they don't actually have any muscle. Their main muscles that power the wings don't attach directly to the wing, which is really weird, right? You beat a wing up and down and you don't directly attach to it. Instead, the muscle that's producing the downstroke for this wing, it has its origin back here and it has its insertion point up here. And if you look at the exoskeletal plate here, so this is an insect, so it has an exoskeleton. You can see the skeletal plate deforming in this long axis. And that deformation is propagated down to the wing. So we're going to take this thorax out, this part of the body in the middle, and we're going to measure the work that that downstroke muscle produces. So that's going to be this DLM muscle here that goes from the back side to the front side. And you can actually see it flexing against the exoskeleton here, changing length. Okay. So we want to measure the power output from that DLM. All right. And so if we take a cross section, here's a nice CT scan of the musculature inside that thorax that was taken by an IMSI summer student last year, Joanna Baker. And this large green muscle in the middle, sort of pale green muscle in the middle that's spinning around, the really giant one, is the downstroke muscle. And so that's the one that reaches from here to here and is going to contract to produce the downstroke. And this is a pretty cool muscle because it effectively acts as a single motor unit. It does have different subunits and a couple of motor neurons, but they all tend to be synchronously activated. And so you can treat this whole muscle as a single effective motor unit. And it's activated every wing stroke in these kinds of insects. And so here's an example of how we can measure the activity from the muscles. This is if we put little silver wires into the downstroke muscle and a bunch of other muscles. There's actually 21 wires recording 10 muscles simultaneously as the animal is flapping on a force torque transducer. Yeah.
Simon, this is Bert. I think whatever you're showing on your screen might not be the same thing you're talking about. Or whatever we're seeing on the slides is still that.
That's too bad. Slide. Okay, hold on. All right. Do you see? Yes, now you see the video. Okay, let me just back up for a second. So because you missed that first intro slide, thank you for interrupting, Bert, so that we can do this properly. Here's that thorax here that I was talking about, that exoskeleton. And the muscle goes from the back side to the front side and deforms. Is that better? Yeah, I see Manny nodding. And I can see it on my screen too now. Okay, so this muscle doesn't attach directly to the wings. Instead, it deforms and indirect the exoskeletal plate like this, and it indirectly moves the wings up and down. And so here's a CT scan, the CT scan I was meaning by Joanna Baker. This dark green muscle in the middle, that is the big downstroke muscle we're going to record from. And the cool thing about that muscle is that it's the primary power muscle, and it has effectively a one-to-one spiking relationship between the motor neurons and the muscle, and it acts like one big motor unit. Okay. So that's the muscle we're going to try and do a work loop from. Okay, and then here's a video of how we collect those EMGs to know what the activation of those muscles are. This is 21 wires placed into the moth by Rachel and Joy, and recording the activity of all of these different, of all of the different muscles. And the 2 wires up here are measuring the activity of that main power muscle. And so this muscle animal's on a force torque transducer. This is how we do the behavior in a tethered environment here. Okay, and so just a static image again. So now I've changed the color. Sorry, the big pink muscle is the big downstroke muscle, and that's the one that we're going to be recording, that we're going to be looking at the force from. And we have to do these EMGs to know when in that length cycle to stimulate the muscle to get to measure the right amount of force. Okay, so we're going to take that muscle out. We're going to change its length in the normal pattern that it would experience. And you can sort of see that here in this animation by Andrew Montcastle. If we look inside the thorax, there'll be this big dark red muscle. And as it contracts, it's going to change length. And the cool thing is that on each wing stroke, it gets a single pulse of activation. Okay, so as this big dark muscle contracts, the wings are going to move up and down. So we can measure that magnitude of that length change. We are going to, in our experiment, we're going to play in the length change. We're going to play in the activation, and we're going to measure the force such that we can then plot force versus length and create a work loop. So when I take you over to the lab, what you're going to see is we're going to take this muscle out, and we're going to mount it in this apparatus on the right, which has an ergometer, which is a force measurement device that allows us to also change the length of the muscle. So this is also sometimes called a muscle lever. We're going to impale the thorax on those little spikes that stick down. We're going to drip some saline on it to keep the muscle alive. We're going to mount it in there between the ergometer and this rigid mounting plate on the right, which is just a custom 3D printed piece. And then we're going to measure the forces with the controller for that. So first, we're going to drip on the saline with this peristaltic pump. We're going to control the temperature of the saline with the temperature controller. Then we have just a coolant for controlling that temperature. I'm just orienting you to all the pieces of equipment that you're going to see. And then we have a stimulator to stimulate the muscle. And then on the other side, we have the ergometer controller. And this is going to have a number of cables plugged into it that allow us to, and we're going to talk to it with MATLAB. And we're going to say, okay, move the muscle in this particular length trajectory and measure the force that it's producing in response to that length, the change. And in the background there, you see IMSI summer student Luke Marsh from last year. So this is pictures that I took last year. So he won't be around this year. Okay, so I'm going to switch now to the camera on my iPad, and I'm going to take you over there so that we can go see Casey doing the experiment. So I'll stop this, turn this video off, turn this video on. Actually, I'm going to turn it off while I walk over there because I don't want you to get motion sick. We'll go over and see Casey. And again, this is going to be a real experiment, so it may or may not work in real time, but you'll at least get to see how we set everything up. So we're walking over to the lab now. I'm also going to take out my headset so you can hear Casey talking. All right, so here's Casey now. Hi, everybody. Can you guys, let me make sure that they can hear us. Hold on. Can somebody tell us if you can hear us?
Yes, we can hear you.
Okay, great. And you can hear Casey?
Yes, can everybody hear me?
Yes.
Yeah.
Great.
Okay,
all right,
perfect.
Here we go.
So now we have the thorax that's been separated from the moth. As you can see, it's still twitching like this.
Oh, we still.
Oh, we might need to change the camera view.
Yeah, I changed the camera view to my other view. So if you have it pinned, you should be now looking at my camera here. Let's see. Okay, hold on. There we go.
Okay.
There we go.
Everybody should be able to see that. Everybody can see Casey now here? No.
Yes.
Good.
Okay, perfect.
Go ahead, Casey.
Okay, so now we have the thorax. As you can see, it's still twitching. So what we need to do in order for us to directly stim the muscle is to go through and cut the ganglion on the ventral side of this. And sometimes you have to cut through some of the excess that's there. But I cut the ganglion, so now the thorax is no longer twitching on its own because we're going to stim it ourselves. Actually, I have to make a couple more cuts.
So the muscle, since we've isolated this from the brain, with invertebrates, when you cut the head off of the animal, it usually disinhibits.
So now what we're going to do is fix the muscle on either side. So on the posterior side, we're going to insert these prongs with this epoxy right here into this grease right here, and we have to get the angle right before we fully insert it. There we go. And then we're going to remove the excess glue so it dries quicker, because again, this experiment is kind of time sensitive.
Hold it in one place.
Yeah, sure. And so now I'm going to just apply a little bit of baking soda right here to get it to dry a little quicker. Then I can attach it to our mount. So this mount is attached to this lever system, and essentially it's capable of measuring the force output applied to this lever. And it's perfectly calibrated to the length of the lever so that the force is correct. So now I'm going to turn it on and make sure that my length is at about 0, so I have room to work with on either side. And I'm also going to adjust the thorax to make sure it's in the proper position. We will tighten this once again because it needs to be fixed. We won't get the proper force output if we don't tighten everything and adhere everything so that the muscle is at a fixed length. Okay.
Hold on for just a second, Casey. I'm
Yes.
just gonna set this so that I can just took over everybody's screen for a second. Okay. Okay. Good. Can everybody still see now?
Yes.
Okay. Good.
Okay, perfect. So now we have this 3D piece right here, which needs some glue. So I'm just gonna sneak past you, Simon. So this is gonna need some glue. I also need to, sorry guys. Okay, I also need to file this down a little bit so that there's no scales. Moths have scales instead of like feathers like a bird would have or something. So I filed this down so it's easier to glue it to this 3D piece, which is fixed. Once again, we're fixing both at the ends. So then we get some glue right in there on the end of the piece. And then, yes, go ahead, Simon.
This is all the advantage of having the skeleton on the outside.
Right.
So we're setting everything up, and because the skeleton is on the outside, it also holds the muscle at its proper length until we get it all mounted in properly. And then we'll release tension on the muscle to isolate it from the exoskeleton.
So now I'm moving the lever on the force transducer here. It's not quite there. There we go. So now we're attaching it to this point. I need to now, remove the excess glue once again so that it adheres to the muscle properly. Okay. There we go. Okay, and now I will set the baking soda once again right on top of the thorax. I want to blow away any of the excess right there. And so now it's a little bit of a waiting game. So we have the force set to somewhat negative force because this is the muscle is now working against the lever in this direction or in the lengthening direction. So whenever the muscle contracts, it's going to create a positive force on the lever because when muscles contract, they're doing positive work on the system that they're in. So once again, we have this at about a negative force. While we wait for the glue to dry, I can go ahead and pierce the exoskeleton to prep for the electrodes. So once again, the exoskeleton is still intact, but I need to make these small insertions right here on the anterior side of the thorax so that later when I'm inserting my electrodes, it's not so difficult. So I'll do that on either side because I have 2 ground electrodes and 2 quote unquote hot electrodes, but right there. I make 2 insertions. Now we wait just a little bit. While we're waiting, the next step will be to make some cuts, and I'll make some cuts right here, closer to the posterior side, right above the DLM. So the DLM is right next to the top of the exoskeleton. So I have to be very careful when I'm cutting through the top portion right there, because I don't want to accidentally cut some of the muscle. Inevitably, sometimes I'll cut through some of the muscle, but it's very important that we separate the exoskeleton so that the muscle itself is responsible for any passive or positive work that's happening. And we really want active work. We want an active work loop. We want to create force just with the muscle. So we're just gonna see, it's pretty solid right there. So the next and one of the most important steps in this experiment is to zero the force. This is so that we get to the resting length of the muscle. Later, I'll talk about the operating length of the muscle, but that's after the electrodes have been inserted. So we need to get the muscle to its resting length. So I'm going to get this force over here as close to zero as possible. And it's a little bit positive, but that's good because it means the glue is working. Can be tricky. So that's a slightly positive force right there, but it's as close to zero as we can get. It's actually dropped negative a little bit. Actually, slightly adjust it. Yes, it can be very finicky because we're adjusting the length to try and get the force output to be what we want it, but it's close enough to zero. So now the next step is to make careful incisions onto the exoskeleton so that we separate the muscle from the exoskeleton. So
we're going to keep the origin and the insertion of the muscle. And what we're really doing here is, because the muscle is usually having to do work against the exoskeleton, we want to release that so we can just measure the work of the muscle by itself, as opposed to measuring the work of the muscle plus the exoskeleton. We do sometimes want to measure that as well, in which case we could leave that intact. It's sort of like the difference of doing a muscle versus a muscle tendon unit. But in this case, the springy part is in parallel with the muscle rather than in series.
So another important step right here is, so I've cut the exoskeleton on the top, but I also really need to cut the wing hinges. These wing hinges create a lot of passive force, so I need to cut them on either side of the muscle. This side is harder because I don't have as good of an angle, but I cut through it. So now I've cut through the top and both wing hinges on both sides, and I can also cut through down here. So I need to cut through the ventral side, just to make sure one last time that we don't have any passive force. And so I'm going to cut through. You can be a lot more liberal with this bottom side because the DLM, once again, is located very close to the top of the thorax. So I can even cut some of this excess material off. So what I'll often do is completely cut this part off. Making sure still not to go too high and accidentally cutting the exoskeleton, or I mean accidentally cutting the DLM, dorsal longitudinal muscle at the top, which is responsible for downstroke and flight. So now the next most important step is running the saline drip that I've prepared. So it's just going to take a few seconds here. Okay, so I'll slow it down. Now we have a saline drip slowly running over the top of this muscle. The saline is in coordinates or ordinance with the physiology of the muscle. So we have the right salts and sucrose levels in there and also the right pH. So we've measured out this saline so that it keeps the muscle alive as long as possible. And once we get the drip going, the muscle will stay alive. And we'll leave the drip cold. So now let me orient you to some of the equipment we're working with. So once again, this is the force meter. We're not reading it out into the computer. We're actually reading it onto this oscilloscope. So whenever we're going to see potentially a twitch from the muscle, we'll see a spike here.
And why did the force now change away from zero?
The force changed away from zero because we're slightly below zero right here on the
So now we release that exoskeleton.
Right.
So now the resisting force of the exoskeleton is not there. That's why we needed to set the 0 point for the muscle
Right.
before doing any of that clipping of the exoskeleton.
So now these are my electrodes. They're hooked up to this pulse stimulator. Now this stimulator is specifically used for biological research. And essentially, there's a bunch of settings on here so that we get the correct pulse that we want. We're at 6 volts. We're at millisecond burst width. And then we have this little lever here that whenever I'm going to pull it, it should twitch the muscle. So first I have to insert my electrodes into the muscle. So here I have on this black heat shrink right here, I have my ground electrodes. So those two will be on the same side of the muscle. We're going to put those on the posterior side. It doesn't really matter because it just needs a voltage drop across it, the muscle. But I'll insert them where I made my incisions previously when I was cutting around the muscle.
And I'm going to let Casey do this carefully because this takes a lot of management. While he's doing that, I'm just going to show you that. So we oftentimes get a question of why we're not doing this in like a bath or why we're not doing it in a larger sort of tabletop rig. And the reason is if you look at this setup, it's very narrow in profile except at the top. And that's because this whole work loop setup will take up to Argonne National Lab and we'll slide the whole thing into the X-ray beam line and shoot X-rays through the muscle in this direction in and out of your screen in order to measure the molecular properties of the muscle at the same time that we're doing the work loops. So that's why we use this kind of unusually shaped rig.
Okay, so now we have the electrodes inserted. And so we'll turn on the machine. You might see a twitch because there can sometimes be a transient voltage. No twitch there, but that's good because we really shouldn't see a twitch. And then we have a timing overlap for some reason. Oh, correct. I did a tennis switch earlier. So, okay, so now we're at single pulse. So we can just try and see if Simon can get real
switch
close
sides with you. We're actually going to watch the oscilloscope. So we're going to look for the force, but we'll watch the prep first.
Correct.
So now we're going to send a pulse of activation. So this is like a twitch experiment, right? And so if you watch one more time, you might see a very small twitch of the electrode.
See the electrode.
And if you look at the force on the oscilloscope, we're seeing a nice twitch response.
There you go.
Every time Casey flicks the switch on the
So
simulator.
once again, the force output. So this is the force out right here. We have it plugged into the oscilloscope, so you can. This is the voltage that's represented by the force. So we're getting a voltage every time this meter moves. So even if I put a little jump in there, I touch the lever, it gives a little force right there. So once again, I'll twitch the prep one more time. So right there. And then I guess one more thing we could show you is an active work loop experiment. So to orient you just a little bit here, we have the amplitude at which the lever is going to move. So right here, we're basically...
Casey, we're a little over time, so let's just show them, and then we'll go to the experiment.
Sounds good.
We're going to just run a work loop with sort of natural in vivo conditions here. And if you watch, the whole thing will get pulsed, and it'll go by really quick right there, because this muscle is usually operating at 25 hertz, 25 times a second. So what you're seeing in this quick experiment is an example of 10 wing strokes happening right about now. There we go. So very briefly, and we see a force trace that comes out. All right, so what we have now is we have we've uploaded data from this experiment taken earlier with a different prep, and there's 3 files in that CSV folder. And what we want you to do is pull down those data files, and in the next 15 minutes or so, we want you to plot force versus length for the 3 different work loops that we've included. And what we've done is we've stimulated the muscle at different phases such that one of those work loops should be positive, one of them should be negative, and one of them should be doing net zero work. And so your quiz for this workshop is to tell us which of the 3 files is the positive work loop, which one's the negative work loop, and which one's the zero work loop. And there's the data actually taken from this moth muscle that you just saw the demo from. So let's thank Casey. Yay, thank you, Casey. And we'll go over and give you guys about 15 minutes to do that. And then Casey's going to pop on his computer and show you the plotted work loops at the end. Does anyone want to take a shot at saying which file is which one? Anyone want to tell us which file is the positive work loop? Brave souls out there.
Yeah, we have a tentative answer from Cheyenne. All right, Casey, why don't you show us?
All right, well, I'll go ahead and share my screen. It looks like you all, everyone who's commenting in the chat has good intuition. However, it's possible that your intuition has led you slightly astray. So, whoever said that so first before I fully get into the work loops here, first I'll just take us through the data here. So this first representation of the data is just the length, the force, and everybody can see my screen, right?
Yeah, but let's
Okay.
do this. We only have like 2 minutes left. So.
Okay, we have 2 minutes. Okay, well, these are just representations of the length of force and the stim over time. So that's for all 3 data points. So then this is the first data point. So this is the work loop we have for this. On these work loops, I have a couple points representing the direction. So green is the start, red is the stop. So as you can see, we have a counterclockwise rotation here at the top of the work loop, and that will lead to a positive work. And then down here, we have a clockwise rotation, so that leads to a negative work. So these works about cancel out, and we get about 0. Here it's 14. This is just an arbitrary integration. So the first work loop is indeed 0. Someone in the comments suggested that. Now, a lot of you suggested that the second point of data has positive work. Now, here, there is a large area under these curves, but as you can see, we're going in the clockwise direction. Yes, we're going in the clockwise direction here, green, yellow, red. And so because positive length change is in this direction, so moving this way as we go negative, that means that this integral over these top curves is actually going to be negative. So this is our negative work loop, and here I've integrated it. I've actually had to include a -1 here to put in our standard for length change. So then
And
finally,
because remember the delta x equals minus delta L. That's
right.
The key trick here, is to get that sign correct. And if you got that incorrect, don't worry, you're not the only one. Last year when we did this, the senior engineer in our team also missed the negative sign on that work group.
So yes, once again, your intuition was correct, but our convention is positive direction is shortening of the muscle. So then our final work loop is so as you can see, once again, that was clockwise. Our final work loop, we have this counterclockwise behavior. There's this small negative work being done right here, but overall we get a positive work. So those are your 3 work loops.
All right, thanks Casey for taking us through those. Casey will post this Jupyter notebook as well, so that you can go through his stuff. If you know your Python code, you can open a Jupyter notebook. I also encourage you to plot those again if you had any issues with those. Thank you all for attending the first workshop. Victoria, when's the next one?
Next one is next week on Thursday. Let me pull up the schedule real quick.
Same place?
Yes, same place, same room. And we will be looking at material properties in biomechanics.
Yeah, and just to thank Casey especially for doing a live experiment. Always challenging to do that. So thank you, Casey.
Thank you, Simon, and thank you everybody for bearing with us through any technical difficulties.
And thanks, Simon, for the nice introduction to work loops. It's very useful to have a very sort of a nice step-by-step walking through. Yep.
If you have any follow-up questions, please feel free to write me and Casey. We're on the IMSI Slack too. Have a good week.
Bye, everyone.